Hello everyone and welcome to our channel MooTechie. A special welcome to all the dairy technologists and students with us today. We're going to explore a crucial phase in bioprocessing, downstream processing. Now let's define downstream processing. Now that the organism has been grown and the product produced, how do we actually get the product? Possibly the most expensive part of the entire process is the extraction and purification of the product. We must separate the product from cells, cell fragments, cell byproducts, and medium constituents. The choice of a downstream process is based on several factors. These include the location of the product in the organism, whether it's intracellular or extracellular. The concentration of the product in the growth medium is also key. We must consider the physical and chemical properties of the product itself, its intended use, and the minimal standard of purity required. The biohazard level of the medium, cells, or product is important, as are the specific impurities present and the market price of the product. Moving on, we will see that we can actually modify the upstream processes to make downstream purification easier. We can select organisms that do not produce undesirable pigments or metabolites. We can modify fermentation conditions so that undesirables are not produced. Precise timing of the harvest is crucial. We can control pH and temperature after harvesting. Adding flocculating agents can help, and we can choose antifoams that don't cause purification problems. Another strategy is using lytic enzymes to aid in cell wall disruption. Next, we explore the overall strategy for recovery and purification of bioproducts. A general flowchart starts with the fermenter. The contents are separated into cells and supernatant. For intracellular products, cell disruption is needed, followed by recovery and purification. For products in the supernatant, we move directly to recovery and purification. The final steps for both paths are crystallization and drying. Now let's look at cell disruption. Disruption means the cell envelope is physically broken, releasing all intracellular components into the surrounding medium. The methods are broadly classified as mechanical and non-mechanical. One mechanical method is ultrasonication using sonicators. It's suitable for bacteria, viruses, and spores in lab-scale suspensions. An electronic generator creates ultrasonic waves, which cause a mechanical oscillation via a titanium probe immersed in the cell suspension. Another mechanical method is milling, which is suitable for continuous operation. It's used for algae, bacteria, and fungi on a large scale, handling up to 2000 kilograms per hour, and can process both liquid and solid feeds. The principle involves a grinding chamber about 80% filled with beads. A shaft with designed discs or impellers rotates at high speeds inside the chamber. The high shearing and impact forces from the beads break the cell walls. Ball milling is another mechanical method, used for solids like frozen cell paste or cells attached to a solid matrix. This is also applicable on a large scale. Homogenization is a mechanical method for suspensions on a large scale. It involves pumping a slurry at very high pressure, up to 1500 bar, through a restricted orifice valve. The cells disrupt due to high liquid shear in the orifice, and the sudden pressure drop upon discharge to atmospheric pressure. Examples include the French press and Golin-Manton homogenizers for lab scale, and the Rani high-pressure homogenizer for large scale. A diagram illustrates the high-pressure orifice through which the slurry is forced. Now, let's examine non-mechanical disruption methods. One way is using chemicals to solubilize components in the cell walls to release the product. The requirements are that the products must be insensitive to the chemicals used, and the chemicals must be easily separable afterwards. Types of chemicals include surfactants like sodium sulfonate and sodium dodecyl sulfate to solubilize lipids, alkali like sodium hydroxide, which is harsher, and organic solvents like toluene, which penetrate lipids and swell the cells. For example, bacteria can be treated with acetone followed by sodium dodecyl sulfate to extract cellular proteins. Another non-mechanical method uses enzymes to lyse cell walls gently to release the product. This is gentle but can be high cost. An example is using lysozyme, a carbohydrase, to lyse the cell walls of bacteria. Osmotic shock is another technique. Osmosis is the transport of water molecules from a high concentration region to a low concentration region when separated by a selective membrane. Water passes through the membrane more easily than other components. When cells are placed into pure water, they swell and can burst due to the osmotic flow of water into them. Cell disruption faces several challenges. There is a risk of heat denaturation damaging the product. Oxidation of the product can occur. Furthermore, disruption leads to the unhindered release of all intracellular products, creating a complex mixture to separate. Returning to the purification strategy flowchart, it shows the fermenter contents undergoing solid-liquid separation. The cells can be routed for cell disruption, which produces cell debris that also needs purification. The supernatant and the products from cell disruption then move to the purification stage, followed by crystallization and drying. Now let's look at methods for separating soluble products. Liquid-liquid extraction relies on the difference in a product's solubility in two immiscible liquids. It's applicable for separating inhibitory fermentation products like ethanol and acetone butanol from broth, and for antibiotics using solvents like amyl acetate. Requirements for liquid extractants are that they be non-toxic, selective, inexpensive, immiscible with the fermentation broth, and have a high distribution coefficient Kd. Kd equals YL divided by XH, where YL and XH are the concentrations of the solute in the light organic phase and the heavy fermentation broth phase respectively. For example, penicillin is extracted from broth using isoamyl acetate where Kd can reach 50. When fermentation broth contains more than one component, the selectivity coefficient, beta, becomes important. Beta_I equals K_D_I divided by K_D_J, where K_D_I and K_D_J are the distribution coefficients of components I and J. The higher the value of beta_I is, the easier it is to separate I from J. pH also has an effect. For instance, at low pH below 4, penicillin can be separated from impurities like acetic acid by moving to the organic amyl acetate phase. Precipitation is another method. It reduces the product's solubility in the fermentation broth by adding chemicals. This is applicable for separating proteins or antibiotics from the broth. Methods of precipitation include salting out by adding inorganic salts like ammonium sulfate or sodium sulfate to increase ionic strength. Factors like pH and temperature affect this. For example, the solubility of hemoglobin decreases with increasing amounts of ammonium sulfate. The added salts interact more strongly with water, causing the proteins to precipitate. This method is inexpensive. Another method is isoelectric precipitation, where a protein is precipitated at its isoelectric point. For example, the isoelectric point of cytochrome C is 5.6. Adsorption involves adsorbing a soluble product from the fermentation broth onto solids. Approaches include physical adsorption using activated carbon, and ion exchange using resins like a carboxylic acid cation exchange resin for recovering streptomycin. Adsorption capacity is the mass of solute adsorbed per unit mass of adsorbent. It is affected by properties of the adsorbent, like its functional groups and surface properties, and by properties of the solution, like solute type, pH, ionic strength, and temperature. This method relies on the difference in affinity of the product for the solid and liquid phases, and is applicable for soluble products from dilute fermentations. Membrane separation is another key technique. Microfiltration uses membranes with pore sizes from 0.1 to 10 micrometers to separate bacterial and yeast cells. Ultrafiltration is for macromolecules with molecular weights between 2000 and 500,000. Dialysis removes low molecular weight solutes like organic acids and inorganic ions. Reverse osmosis applies pressure to drive water from a low to high concentration region and is for molecules with molecular weights less than 300. The common features of these methods are the use of a membrane and pressure as the driving force. Chromatography separates solutes based on their different rates of movement through a column packed with adsorbent material. The principles involve a stationary phase, which can be an adsorbent, ion exchange resin, porous solid or gel, and a mobile phase, which is the solution containing the solutes and the eluent that carries it through the stationary phase. It is applicable for separating proteins and organic compounds. In the method, a solution containing several solutes is injected into the column followed by the eluent. Each solute moves at a rate proportional to its relative affinity for the stationary phase and comes out as a separated band at the end of the column. A diagram from M. Schuller's Bioprocess engineering illustrates this, showing different solute bands separating. The mechanism of chromatography is similar to adsorption as it involves solute-adsorbent interaction. However, it is different because chromatography is based on the different rate of movement of the solute in the column, while adsorption is based on capturing one solute on the adsorbent to separate it from others. Electrophoresis separates charged solutes based on their specific migration rates in an electrical field. Positively charged solutes are attracted to the cathode, and negatively charged solutes are attracted to the anode. Factors affecting separation include electric field strength, the electric charge of the solutes, the viscosity of the liquid, and the particle size. It is applicable for protein separation. A diagram of protein electrophoresis shows a gel with bands corresponding to proteins of different molecular weights, labeled in kilodaltons, such as 250, 160, down to 25. Returning to the final stages in the purification strategy, we have crystallization and drying. Crystallization is often the last step in producing highly purified products like antibiotics. It involves creating a supersaturated solution, often at low temperatures, and then separating the crystals by filtration. Drying is used to remove solvent from the purified wet product, whether it's a crystal or a dissolved solute. Vacuum tray dryers are used for pharmaceutical products. Freeze drying or lyophilization works by sublimation and is used for antibiotics, enzymes, and bacteria. Spray drying is used for heat-sensitive materials. Finally, let's summarize separation and purification. For liquid-solid separation, we have filtration methods like rotary vacuum drum filters and micro/ultrafiltration and centrifugation. For cell disruption (EE), we have mechanical methods like ultrasonication, milling, and homogenization, and non-mechanical methods like chemicals, enzymes, and osmotic shock. For the separation of soluble products, we have liquid-liquid extraction, precipitation, adsorption, membrane separation like ultrafiltration and reverse osmosis, chromatography, and electrophoresis. The process concludes with crystallization and drying. Thank you for joining this detailed session on downstream processing. We've covered the essential steps and methods for recovering and purifying valuable products from fermentation, from initial cell disruption to final crystallization and drying. Understanding this process is key to bringing biotechnological products to market. Thank you. See you in the next class.